Now we're going to move on to antagonistic coevolution. And this is one that involves sort of predator-prey interactions. And then the next thing we'll talk about is sort of antagonistic coevolution between host and parasites. Okay. Hopefully, I don't remember which is a good thing. One of these is a viceroy, one of these is a monarch butterfly. I believe, I don't know. Do you know? It doesn't matter. They're both kind of, I think this doesn't look like the right host plant that a monarch would be on. This one doesn't either, but I think this is the, I'm not sure. This is the viceroy monarch. Okay. The key thing is they look kind of alike, don't they? And it turns out these things are not in the same genus. They're in different genera, and they've presumably converged on a similar coloration independently. And this is what we believe is an example of mimicry. And do you know, obviously monarch butterflies are very endangered. There are a lot of reasons why. They have a very limited range in Mexico where they're found, but also a lot of their native host plants in the United States and Canada are becoming harder and harder to find. And it turns out that, what do you think this bright coloration's for? And your book has a really good one about newts, but I decided to focus on this one. What do you think that bright coloration is for? Yeah, it's actually a signal to a predator that I'm poisonous. This is what we call aposematic coloration. I'm not going to ask you, you don't have to worry about this, but this is an example of bright coloration that's associated with toxicity. And it's a very effective signal to predators, even naive ones, that basically there's often an innate avoidance of things with bright coloration. Or if you immediately taste it, you very quickly learn, like those newts that are some of the most toxic things imaginable that are talked about in your textbook. Predators have learned very quickly to avoid eating things with that coloration pattern. Okay, so it was always initially thought that, so what this involves is this is an interaction between a predator, primarily bird predators, and these are the potential prey, okay? And so viceroys, we'll just say this is the viceroy. Viceroys were always believed to be what are called non-toxic, okay? And they were mimicking the toxic monarch. And I'll come back, I'll explain this. This is kind of the classic example of Batesian mimicry. In the newt, there's some examples of that in the newt, where there are some species that are mimicking the coloration even though they don't have the toxicity. And so they've kind of, evolved this defense mechanism and taking advantage of this coloration to fool the predator, okay? So this is what was always believed. So, and there were a lot of good reasons to believe that obviously monarchs are toxic. And the reason is if you feed them to a bird and you give them the abdomen, the birds gag right away. And it turns out they get these monarchs, when on larvae, they feed on these milkweeds. They have these really nasty secondary chemical compounds called glycosides. And it turns out they ingest these, when they eat the host plant, they ingest these glycosides, they incorporate those toxins into their tissues, and that's what confers the toxicity. And that's where most things tend, in general, sometimes they can produce them innately, but a lot of times, especially in insects, they get this toxicity from the host plant that they're eating, okay? So this was always believed to be the toxic, it was called the model, and then the viceroy was the mimic that is taking advantage of the situation. Okay. So let's think about this. Imagine you went into a population and you found both of these species present. And the viceroy, which has the bright coloration, but it's edible under this model. What if there were a bunch of these? Let's say there were 95% of the individuals in a population were viceroys and only 5% were monarchs. How do you think that would work out? Would that work? Imagine be a bird. You're a predator, right? and you at random go in and say, I'm gonna eat just at random one of these things, and the highest likelihood is you're going to eat the Viceroy, right? What are you now going to associate the coloration with? Being edible, right? The wrong thing. So Batesian mimicry only works under really kind of limited conditions. And what do you think the frequency of the mimic has to be? It has to be really low compared to the model. So the Batesian mimics, the Viceroys have to be fairly rare, and these have to be pretty common because that predator has to get reinforced by that. Oftentimes they'll eat, they'll gag, and guess they'd never eat it again, right? So they have to get that association between the coloration and being inedible. And that only works if the model, the toxic one, is the common one. So everybody always thought Batesian mimicry was really hard to evolve. And everybody believed that this was an example of Batesian mimicry. Guess what? They were wrong for hundreds of years because nobody tested it. So actually what they did, and this is what I said here, Batesian mimicry is really unstable. It's a really hard thing to get it to work because predator learning only works if the mimic, that's if the mimic is at very low frequency. There were also a lot of indications based on what viceroys were eating, and they knew something about the host plants. They were thinking, I bet that seems to be, that's a smelly plant. Usually when you eat a smelly plant, I shouldn't say this. Okay. If you look at like iceberg lettuce versus arugula, right? Iceberg lettuce has no flavor, it has very few secondary chemical compounds. Arugula and all these other things have a lot. So it turns out there were many indications that the Viceroy's bite might be toxic too. So the other kind of mimicry is what's called Mullerian mimicry, and that's where both of the, in this case, butterfly species, are both toxic. So they're kind of reinforcing each other, that actually both of them are toxic. It's a very simple system, right, where if bright coloration is always associated with toxicity, it should be pretty stable. So my question, how do you test that? How would you distinguish between the Viceroy being a Batesian mimic or whether they're actually Mullerian mimics? Can you think of a real simple thing to do that it took 1995 to do? Yeah, I wouldn't even do genetic. Well, you could. You could look at the secondary chemical compound. I'd eat it. Or have a bird eat it. Give them a choice, right? Give a blue jay, these are the common predators of these things, or at least will try to eat them. Give them a choice and see what they do. What do you think? Did I put the data? I don't think I put the data up here. No. If you give a choice between a blue jay, and you do this multiple times, multiple blue jays, you give them a choice of something that's edible, and then give them a choice of also eating a monarch and a viceroy, what result would be consistent with them being Mullerian mimics in terms of what percentage of viceroys and monarchs that they ate? Huh? Yeah, they shouldn't eat many, they should not eat many of the viceroys or monarchs, and probably they should reject them at about equal rates, right? They would be bad things. What would be true if they were Batesian mimics? And you did it blind, you just gave them a choice, and they gave them an abdomen of a viceroy and a monarch. What would be consistent with Batesian mimicry? What would they eat more of? Of the viceroy, okay? So this is a real simple experiment to basically, a viceroy is edible, right, under the Batesian mimicry, so you would expect them to eat more of the Batesian mimic. And they took off all the wings and all the, I'm not going to go into all the details of how they did it, but guess what they found? They didn't eat either one, or they, yeah. So this is a really good question. How do you know it's some sort of mimicry? How do we know it's some sort of mimicry? one of the ways we know is that they're in different genera, right? And so you can actually look at the coloration patterns of all the butterflies in the Viceroy genus, and you can look at all the coloration patterns in the Monarch genus, right? And these are the ones that are the bright ones. And so the idea is they've converged and have sort of mimicked one another. Okay. They've kind of converged on this. They're not exactly the same, believe me. There's a little bit of difference, but they have kind of the orange and the black and the white spotting. It's not exactly the same, but it's kind of converged to a similar coloration pattern. And so the idea here is these two would get a really big benefit from converging on that because it would signal to the predator, right, we're both toxic. And so it turns out what they found was they weren't Batesian mimics, they were Müllerian mimics. And they did this in 1995. Okay. Let's leave, we're going to talk about parasite virulence next time. And what we're going to talk about is, we're going to talk about how parasite nastiness or virulence evolves, and we're going to look at an example between a virus and a rabbit host as an example. It always doesn't go to low virulence. So anyway, we'll get you thinking like a parasite. Okay. Has everybody turned in the homework? Okay, because I'm about ready to go over it. I got to look at the numbers too. I'll just write this on the board. You could do this a number of ways. Okay. So the first thing you want to do this formula in two different habitats. Did you get that? Okay. So the first habitat that we talked about is one habitat where parasitoid wasps are present. Okay? And here they're absent. So in one habitat, parasitoid wasps are common. They lay their eggs inside bee larvae and kill the bee larvae. So these were parasitoid wasps. And there's a high risk of parasitism of bee larvae by these wasps. Female workers increase the average number of sisters produced in the colony by 30 individuals. Okay? So what's the benefit in this habitat? Yep. So B equals 30. You increase the number of your sisters by 30. There's a real benefit to being a worker and helping out. Okay. What's R in this case? And you could do it either way, but who's the primary benefit in this haplodiploid? 3/4, right? The sisters are getting the benefit. Or you could say the mother. If you put half, I'll give you, because the outcome's the same. But okay. Now this is what I think is the hard part. What's the cost? And the way you have to think about it, how would an individual in that habitat do if they went off and reproduced on their own? How many direct descendants are they going to get when they go off on your own? So did I give you that number? Whereas solitary breeders produce an average of 5 offspring in the environment. So that's 5. So the way to think about it, what I presented in each environment, you can actually do both. So this was hard, I understand this, okay? So when you put this together, what do you get? Is that greater than 5? Yes. Okay. So what's favored here? Being a solitary breeder or being a eusocial? Yep. Eusociality is favored. And there's another way to do this. I'm not going to go through it, but one person actually emailed it to me and did it the other way. Okay. So, does it look like having being eusocial is really helpful in an environment with a lot of parasitoids? Yep, it's really good to be in a social group. How about when a parasitoid wasp is absent? Maybe there's something better to do? Go off on your own. Okay. So in another habitat where there are no parasitoids wasps, helpers increase the average number of sisters produced in the colony by 10 individuals. Okay? And it doesn't matter. We'll just say 3/4. And what's the cost by being eusocial in that kind of environment? 25. So what you can see, you can, and I'm not sure this is real, but those are the numbers I put down. Okay? Is that true? Whoops. That is not true. So what should be favored here, being eusocial or solitary? Yeah. So the idea here is solitary breeding would be favored. And the idea here is you're not dealing with the risk of your larvae being parasitized. You don't need a big group to do it. And there must be some real cost to kind of being in a big group, right, in that sort of environment. So it's actually better to kind of go off on your own and produce your own direct descendants rather than being part of a big social group. Okay? Okay. So that's kind of what I was looking for. Did anybody come close? Did anybody get kind of near that? Okay, good. Okay. I'll look through them, and if it looks like it's going to need to be bonus points, then I'll go with bonus points. But okay. Does that was I knew that would be kind of challenging, but does that make sense how to now do that? So would you like something like this on the exam? Okay. Well, yeah, now that you know how to do it, right? So, I mean, it won't be exactly like this, but hopefully what this reinforced is you got to think about the costs and benefits of social group living versus solitary living and how this enemy can influence it. That's the way to think about it. Okay. Okay. That's it.